Hello class, this is CSE 5250, section 60, week 4, fall 2023. Last week we started to look at OpenMP. We looked at how we can parallelize for loops, and we did that with an example program that is a implementation of the trapezoidal rule found in calculus. The trapezoidal rule is a means of estimating the area under a curve so that we can so it's a means of estimating the area under a curve. The idea is if you use finer and finer trapezoids, you would get a better and better estimate. And if you did that with infinitely many trapezoids, you would get an exact answer. And it's from there we would get a definition defined using an integral. So you don't have to do an infinite sum anymore. So this is going to be section 5.5 in the textbook. There is another way of parallelizing our trapezoidal rule program. And if you ask me, it is my favorite way of parallelizing for loops. So, it is the parallel for directive. For this to work, we need to start with a version of the trapezoidal rule program that has no parallelization at all. So, we start with this program here. This program has no parallelization. Okay, it does take in a thread count as a command line argument, but we're not really doing anything with it. If anything, that's the only thing we have to do to the program to make it parallelized. So, we have our thread count that we're not doing anything with just yet. We have our scanfs function that is taking in our three values of our start point, our end point, and the number of trapezoids we want. We call our trap function here, and then that estimates the area under a curve that we call using the f function. We're just using x squared as our function for simplicity's sake, but in theory it could be any function that is said to be well behaved. So basically, most, if not all, polynomials in existence, and certain exponentials as well. So, if you remember from last week, we had to parallelize the for loop ourselves by specifying a start and end point. So this was local A, local B, local N. We have to start over because the parallel for loop, we don't have to specify any local A, local B, local N ourselves. In fact, all we really got to do is slap in the parallel OMP, the pragma OMP parallel for directive. That's it. It's on lines 36 and 37. Pragma OMP parallel for, and then we have the number of threads clause here. We have a backslash because we ran out of room and had to continue on the next line. And then we have our reduction clause as before. That's specifying addition as a reduction operation that we are applying repeatedly to our reduction variable of a prox. And that's it. That's all we have to do. And just like that, our program is parallelized. The only other change we had to do was make it so that the program can take in a command line argument in the form of a thread count. But that is it. So, how does this work behind the scenes? Well, what happens is the for loop is divided into however many iterations there are. Let's say there are 100 for loop iterations and there are 4 threads. Keeping in mind that indexing starts at 0, the 0th thread gets the first 25 for loop iterations, so iterations 0 to 24. Thread 1 gets iterations 25 to 49. Thread 2 gets iterations 51 to 74. No, 50 to 74. Thread 2 got 25 to 49. And thread 3 gets the last 25 loop iterations. Those are numbered 75 to 99. This is the default partitioning that is typically done for most systems that implement OpenMP. This is a block partitioning. And if you are absolutely sure that the partitioning, if you are absolutely sure that this partitioning is okay, say every for loop iteration roughly does the same amount of work, then you can just roll with this and it would be good. However, if you have a situation where the time it takes to execute a for loop iteration increases over time, or even decreases, or worse, you don't know how much time it would take at all, then you might need to do something different. You might need to do something that is different from using this default block partitioning. We'll get into that in a little bit. But first, I want to get into a few caveats. What can you not do with the parallel for directive? Or rather, what loops can OpenMP not parallelize? Well, there are quite a few. OpenMP cannot parallelize do-while loops. It cannot parallelize while loops. It cannot parallelize for loops whose number of iterations cannot be determined, and it cannot parallelize for loops that have a break in the loop. This infinite loop has an undeterminable it has a number of for loop iterations that can't be determined. Well, I guess technically it can, but the variables, our integers, would max out at what? 2.1 mil or 9 quintillion, depending on the size. And you could be theoretically iterating even more than that. So we cannot parallelize this infinite loop here. The for loop with nothing in the parentheses, but nothing but semicolons. We cannot parallelize a for loop that has a break in the middle, because if we don't know when this thing will break, we cannot parallelize the for loop. OpenMP can only parallelize for loops that are in canonical form here. So, your index must either be a pointer or an integer. Your start and end must also be the compatible type. So if it's an integer, it must also be an integer. If it's a pointer, it must also be a pointer. Oh, and the index at the end of a for loop is typically something like index plus plus, or plus plus index, or index plus equals some other value. Whatever we have here, that must be the only place in which we increment index. If we increment it anywhere else, we cannot parallelize the code. So this is the canonical form for loops that OpenMP can parallelize. Okay, that's fine and dandy. That's all fine and dandy, but there are certain for loops that could work, but OpenMP might give the incorrect answer. But before that, what happens if you tried to parallelize this? What happens if you tried to parallelize a for loop that wasn't in canonical form? Well, in most cases, the compiler will just flat out reject it. So this is a linear search algorithm here, and has a return in the middle of the for loop. It would just break out of the loop at that point, and the rule is, if you cannot determine the number of loop iterations it would take to find. If you cannot determine the number of loop iterations it would take to finish the loop, then the for loop would be rejected by the compiler if it had the parallel for directive right before it. We don't know when this for loop is going to break out of the loop. So if we try to compile it, the compiler might throw an error at us. And it'll say, no, I can't parallelize that. However, there are loops that the compiler can take in that shouldn't be parallelized. Here's an example using Fibonacci numbers. Oh, don't worry about my face cam. There's nothing underneath where my face is. So, see? Nothing there. So I'm not accidentally hiding anything. So, if a for loop iteration requires the result of the previous iteration as part of the next iteration's calculation, what we have is a loop carried dependence. The calculation of consecutive Fibonacci numbers is a great example of this. We have an array that has 40 Fibonacci numbers, or it will. We start with the Fibonacci numbers 1 and 1 for the 0th and 1st element. And then we have a for loop that calculates the next Fibonacci after that, the next Fibonacci number after that. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 8 plus 5 is 13, and so on. So, given that the array is given some space in memory, specifically 40 slots of memory, if you were to say jump to the 20th element when you shouldn't, there's gonna be something in there that the for loop will have no problem adding. In fact, I guess that's a hint to your next short answer question. Predict what would happen if you parallelized the first for loop, and then predict what would happen if you parallelized the second for loop. You're parallelizing these for loops one at a time, but you are making a prediction of what would happen. Later on in your first homework assignment, you're going to copy this program, compile it, and run it to see if your predictions were correct. So, for your short answer question, predict what would happen if you parallelized the first for loop. Predict what would happen if you parallelized the second for loop. Remember, these are operations that should be done one at a time. I guess for fun, you could parallelize both for loops to see what happens. I am not asking you to do that as part of your short answer question, but you are welcome to do that just to see what would happen. So when it comes to parallelizing for loops, we need to be aware of these loop carry dependencies. So here is a for loop where we are calculating xi, but that value is being used to calculate yi. That is a data dependency, but it is not a loop carry dependency. That's because the indices here are all I. If it's I minus 1, if one of those is I minus 1, we have a problem. We would then have a loop carry dependency, but since the value in the square brackets are all the same, we do not have a loop carry dependency. In other words, if we were at, say, index 5, we would be calculating the 5th element. I guess it's technically the 6th, but we'd be calculating element 5 in array X and element 5 in array Y. It's not a situation where we are taking the value from the element before that to calculate the next element. If anything, this is calculating pairs of elements that are stored in separate arrays. So, we have no problem parallelizing this code. It's not a loop carry dependence. It is a data dependence, but it's not a loop carry dependence. Here's something that I'm gonna have you do as part of your homework. Or I guess your programming assignment. Your first programming assignment will have you create a program that will estimate the number pi. So here's how it works. We have 1, subtract 1/3, add 1/5, subtract 1/7, add 1/9, subtract 1/11, and so on. We add all of those up. We multiply that number by 4. And that gives us the number pi. If we did this for the, say, first 100 terms, so you would need the first 100 odd numbers. If you did this for the first 100 terms, you would get an approximation of pi. But the idea is, if you did this infinitely, if you did this with infinitely many terms, you would get the exact value of pi. So I can start off with this code here. Once again, there's nothing under my face cam, so don't worry. We can use this code as a starting point. What we'll be taking in is a command line argument for the thread count, but that's only there just to give us a head start with parallelizing the code. We don't really need the thread count just yet. If anything, this is just the same program meant for single-threaded execution. We are calculating the number pi using an infinite summation, but we are cutting it off at some number of terms. It gets a little weird when you have something like this because there's a paradox in math that says if you change the order of terms, you will get a different value. Which sounds absolutely weird. But for our purposes, we are just adding. We were just making this here. We have a for loop. We have variables factor, sum, and n. Factor is our -1 in the infinite sum. Every time we exponentiate that, we will get either 1 or -1. So, our factor will only ever be either 1 or -1. Our sum is going to be our final sum. We are adding rational numbers, fractions. We are adding all of them together, and we are gonna end up with some sort of value that approximates pi. I made the data types doubles because that way we can show up to 18 decimal points of precision. In fact, I would recommend you copy the print statements exactly as how they are, because it's set up specifically so that you can see all 18 decimal places, or thereabouts. Oh yeah, the whole sum needs to be multiplied by 4, because in this infinite sum here, we are actually getting 1/4 the value of pi, when we really should be getting 4 times that value to get the number pi. As a side note, there are people who are advocating that pi should not be the value we should be using, rather it's the number tau. I bring this up because it's an interesting thing that you might hear from time to time regarding the number pi. The argument is this. We see 2 pi a lot in maths, and physics. So we really should be using a value that is 2 times pi. That is called tau. It's like 6.28 dot dot dot. Interesting thing to know that sometimes in math, we just use things arbitrarily. And we just roll with it. That includes using the variable x to mean an unknown value. Anyway, that's enough of a math tangent. We are not concerned with math, we are concerned with making a program that does math. So this program is your starting point, and it is a serial program. What we can do is add in our parallel directive, pragma OMP parallel 4, num threads, thread count, and then we declare our reduction operator and our reduction variable. You can see a problem here already. In fact, I wrote it that aside. We are changing the value factor every for loop iteration. So it goes from factor to negative factor. That is a loop carry dependency. So if we are unlucky, we might screw up our estimation of pi, especially if we were to use multiple threads. If we were to run this with, say, 1,000 threads, we would get values like this. 5.8, 2.975, 3.515. This is the closest one in this example, but it shows you that if you have loop carry dependencies, it can wreak havoc on your results. And this is the same program being run multiple times. Each time we are getting a different answer. Not good. But we can fix it. All we gotta do is remove that dependency here. So here's the thing. The factor is negative every other for loop iteration. So if we go back to our summation, if this is term 0 because we started 0, it's positive. This is term 1, it's negative. Term 2 is positive. Term 3 is negative. So every other term starting at the first term is negative. And every other term and all other terms are positive. So every other term is negative. More specifically, it's the terms that correspond to an odd numbered index that are negative. So this is the first term, this is the third term, this is the 0th term, this is the second term. Every other term is negative. Can't we do modular arithmetic to determine whether we are doing an even numbered for loop iteration, an even indexed for loop iteration, or odd indexed for loop iteration? Yes, we can. And here's how. We add in an if statement with an else. If k, this is the k from our for loop. If k is an odd number, the factor is going to be positive. Otherwise, the factor is going to be negative. And that's the one change we have to make. There is one more thing we have to take into account, and it is the fact that factor is a shared variable. So to be absolutely sure that we've removed all of our loop carry dependencies, we would need to make factor into a private variable. We could just declare it inside the for loop, but another way, especially if you want to minimize rewriting of code, is to just make factor a private variable by using the private clause. Check this out. we have the private clause, and in the parentheses we just say factor, and that is our shared. No, not shared. That is a private variable now. Every thread is going to have its own private copy of factor, and no other thread is going to change it for any other thread. This way, we have eliminated all possible loop carry dependencies. And if we run the program again, we now get the same approximation of pi every time we run the program. 3.14059. It should be 3.14159, but in your programming assignment, I'm asking you to estimate the number pi to 3 decimal places. I may as well show you your homework assignment now. In fact, that is your first homework assignment. Write a parallel program that estimates the number pi using the formula described on page 241. Part 2. Attempting to parallelize the program on page 242 without addressing the loop carry dependencies resulted in an incorrect value of pi when using multiple threads, but we would always get the same result when we did that with one thread. So basically, if we just slapped in this parallel for directive without addressing the fact that that factor is a loop carry dependency, why is it that when we had one thread, it worked? But when we had multiple threads, it didn't work? That's question 2. Question 3 has you going back to this short answer question. For question 3, I want you to run this program, write the program, compile it, run it, and see if your predictions in short answer question 2 was correct. That's part 3. Part 4 has you do a different kind of pi estimation program. I may as well draw it right now. So, just ignore that. New. So this is the pi estimation. This is a different pi estimation program. Say we have a square that is of side length 1. Inside that, we have a dartboard with a circle, a perfect circle. My art skills are kind of poor now. We have a dartboard in a square. We throw darts randomly on the board. The rule is this. We are randomly throwing these darts, and they are uniformly distributed across the board. So, if we take the ratio of darts that are within the circle and divide that by the number of darts that were ever thrown, that ratio is going to be pi over 4 again. So here's how it works. You would need a random number generator that would generate an x and y coordinate within the interval 0, 1. And this is for both x and y. We would then need to... Oh, my mistake. Okay, I'm just gonna put the correct units here. So, it's not a circle of... I may have missaid the units, but here they are. here's the correct units. The radius of the circle is 1, so therefore the side length of the entire box is 2. We are making random numbers within the interval -1 to 1. And that's going to be both our x and y coordinate. We use the distance formula to determine whether these random darts are within the circle itself. So, if the distance from the center of the circle to a dot is greater than 1, that means it's outside the circle. But if it's less than 1, or is by chance exactly 1, if it's, for our purposes, if it's less than 1 or equal to 1, then the dart is considered to be inside the circle. Looks like a clock now. So, this is what's known as a Monte Carlo method because we are using randomness to estimate a constant number. This is programming exercise 5.2, by the way, so I have the textbook here. I'm not sure if you can see that well, but suppose we have darts thrown at a dartboard. This is the Monte Carlo method as described in the textbook. So the textbook actually gives you a starting point for how you would program the for loop. It also makes a few recommendations, such as you may want to use long ints for the number of hits in the circle and the number of tosses to get a reasonable estimate of pi. You're going to want a reduction clause. You'll want to print the result after joining all the threads. So yeah, that is your first programming assignment. It's 4 parts, but only 2 of them require actual programs for you to submit. The other 2, they only really need just okay, so let me just go back and explain what you're going to submit. You are going to submit the source code for the programs, as well as a screenshot of the program running. But for these 2 questions, for question 2, you just have to write what happens. You just have to write a sentence for question 2. For question 3, you just need to submit a screenshot of your program running, and then an explanation of whether your prediction was correct or not. It's only parts 1 and 4 that have you require submitting something. So that's going to be your source code as a .c file, and then a screenshot of your program running. I would recommend JPEG or PNG, just for the sake of consistency. You may also submit your whole assignment as one PDF file, as long as I can easily read the document without having to convert it to some other file format, or I guess convert it from some other file format. As long as I can easily read your thing, you're good to go. This says CSE-5000, it should be 5250. There we are. I have to make some few corrections to your assignment. But this is the gist of your assignment, right here. You are also answering short answer question 2, but part of that question is gonna come back in your first programming assignment. I made it so that the assignment is due within 2 weeks from now, but it's due on the Friday 2 weeks from now. I believe I set that to be October 6th. That is a Friday. And of course, if you have any questions regarding the homework or you need help, you can email me about it, or we can schedule a Zoom meeting as well. Anyway, let's go back to the slides. we were looking at, and again, part 1 of your program assignment has already been done for you. It's just a matter of putting it all together and then running the code. Running the code and getting an approximation of pi that is good to 3 decimal places. And that's the first slide. That's the first set of slides. There is another set of slides. It's basically a few lingering questions that I brought up in the first set of slides. So one of them is regarding the first one is regarding how the parallel for directive divvies up for loop iterations amongst threads. The other one is, what if there are nested for loops? So it's best to show this with a few examples. Bubble sort is a sorting algorithm that features a nested for loop. I guess one thing I could do as well is give you a YouTube link to an animated version of bubble sort. It's called bubble sort because the largest values are set to bubble up to the top of the array. And by the top of the array, I mean the end of the array. Anyway, this requires passes that the outer for loop makes. It looks for the largest element in the array, puts that at the back, puts that at the end. It bubbles that up to the top. Then it finds the next largest element and puts it right before the largest element. And then it repeats with the third largest element, puts it right before the second largest, and so on, and so on, and so on, until the whole array is sorted. That's the outer loop. What does the inner loop do? Well, this is how the bubbling up works. It's going to swap, say, the 0, and it's going to swap elements 0 and 1 if they are out of order. Then it's going to swap elements 1 and 2 if they're out of order. 2 and 3 if they're out of order. 3 and 4 if they're out of order. The idea is we are bubbling up the largest element that we found. And once we've reached the end, we will have found the largest element. It's bubbling it up to the top. Can we parallelize this? Well, here's the thing. The state of the array, what we will have done for the first for loop iteration, we need that for the next for loop iteration. So we have a loop carry dependency, which is the state of the array itself. We will have bubbled up the first largest element to the end of the array once we've done our first for loop iteration of the outermost for loop. So we can't do this out of order, we cannot parallelize it, we have a loop carry dependency. What about the inner for loop? Well, it turns out we can't do that out of order either, because we need to do these consecutive swaps in order, starting from the beginning and ending at the end. The inner for loop has a sequence of steps, and it cannot be done out of order. It must be done with consecutive pairs of elements, starting at the beginning and then ending at the end. So we have another loop carry dependency. Therefore, bubble sort is the kind of program that we cannot parallelize at all. Is there something else we can try? Well, we could try rewriting bubble sort altogether, or we can just give up and try a different sorting algorithm. Odd-even sort, or odd-even transposition sort, also features a nested for loop. Here, we don't swap between every possible pair of consecutive elements. We swap. Those elements are being swapped. It's going to be every other element, but it's going to be swapping with the element to its left or it's right. By every other element, I mean the elements whose index is an odd number. So here's how it works. There are two sets of swaps. The first kind of swap is where every other element swaps with the element to its left, if they're out of order. Then, every other element swaps with the element to its right, if they're out of order. We do this slide to the left, slide to the right, cha-cha real smooth, and then the whole array is sorted. We need two different for loops for this. The swap to the left requires its own for loop, as does swap to the right. We are doing this in two phases. We are gonna call this the even phase and the odd phase. The even phase is the swap to the left, the odd phase is the swap to the right. The outer for loop is doing this phasing thing. So, phase is a number that's being incremented every for loop. If it's even, it's gonna do the even phase where we do the swap to the left. If it's odd, it's gonna do the swap to the right. Cha-cha real smooth. It must be done so that we alternate between the even and the odd phase. So swap to the left, swap to the right, swap to the left, swap to the right, swap to the left, swap to the right. We cannot do this out of order. And for this reason, we have a loop carry dependency with the outer for loops. So we cannot parallelize the outer for loop. However, we can parallelize the inner for loop. So here's the thing. The odd numbered indices in the array are the ones swapping with its buddy on the left or the right. Basically, if you take this example of an unsorted array, 9, 7, 8, 6, 7 is going to swap with 9. But is that going to affect... Okay, so the elements that we're going to be swapping are 7 and 6. They're not going to be swapping with each other, but they are going to be swapping with the value on its left. If I swap 9 with 7, will that affect... Oh, okay. If I swap 9 with 7, will that affect how I swap 8 with 6? No. In fact, I could also swap 8 and 6 first, and it will not affect 9 and 7. Cha-cha really smooth now here. If we can do these kinds of things in any order, then we can do them at the same time. Therefore, we can parallelize the inner for loops. However, there are two loops. That's because we have the swap to the left loop and the swap to the right loop. So whatever solution we have to parallelize this, we need two loops to have parallelized. There are two solutions to this. The first one is the easiest. Just slap in the pragma OMP parallel for directive right before each of the two for loops. This requires a handful of clauses. Don't worry about the default none clause. Just don't worry too much about the default none clause. We're adding that in because the textbook says so. We are declaring A and N to be shared values. We are declaring private values I and temp. And that's it. We've parallelized this even odd sort. There are a few considerations as well. The first solution that we just saw will have the outer for loop execute the inner for loop. The inner for loop forks, executes the loop, executes its loop, and then joins once it's finished. Then the outer loop advances to its next loop iteration, and then the inner for loop executes again with another fork and join. That means there's a fork and join for every for loop iteration of the outer for loop. I guess the best way to imagine this is if every day you had every day you are working at a restaurant, but every day you had this really weird rule that says you had to hire a new crew every day and then fire them at the end of the day. Sounds weird, doesn't it? That's what it sounds like. That's what it looks like when we are doing the fork and join every loop iteration. Can't we just hire one team, one crew, and have them do whatever work for the whole duration of the for loop? Yes, we can. Here's what it looks like. We need to add two directives. Two different directives. One is for the outer for loop, and then the other one is for each of the two inner for loops. So the outer for loop gets this directive: pragma omp parallel num thread strand count, and then backslash because we ran out of room on one line, default none, shared an, private I, temp phase. And that is the outer for loop. The inner for loop is a bit simpler. Pragma omp4. Just pragma omp4, not parallel 4. This is a little bit different, and I'll explain. The second solution will have the outer. The second solution will have the outer for loop execute before the inner for loop. But before it does that, the program forks into a team of threads. This team does not parallelize the outer for loop. Rather, it parallelizes the inner for loop. This team of threads basically waits for a parallel for loop, and that's when the threads, I guess you can say, mobilize to parallelize those parallel for loops. This way, we don't have to do a fork and join every for loop iteration. We only have to do one fork, run the whole program, and then join after we've completed the entire algorithm. So instead of a fork and join every loop iteration of the outer for loop, which would cause a lot of overhead, it might increase our execution times, we'd only have to do one fork before we even start the entire algorithm, and do a join at the end. That's it. So that's one consideration. What if I have nested for loops? The solution is to parallelize the for loops that have no loop carry dependencies. You might have a few situations where there are no for loop carry dependencies in any of your nested for loops. But in that case, I think you would be best. I think it might be best. It might be best to just parallelize the innermost for loop if you have a situation like that. There is a collapse directive, but that isn't mentioned anywhere in the textbook. If you want more guidance on what to do with OpenMP, there are online guides. There is an entire online manual for OpenMP. If it has descriptions on what the collapse directive does, from what I understand, it collapses a nested for loop as though into what's basically a singular for loop. See how powerful OpenMP is? We don't even need to rewrite a whole for loop. The directives will just collapse the whole for loop in for ourselves. We don't need to rewrite anything. We can just add in directives that say, hey, I want this thing to be private, or I want this to be a reduction operation, or I want this thing to be parallelized, but I want the squad to wait before we have a parallel for loop to do. Okay, but maybe the squad wants Okay, but maybe the squad wants to do the same amount of work amongst each thread. So the default assignment of loop iterations is typically a rough form of block partitioning. This is not a program you can try for yourselves. It is a simple for loop where it will say loop iteration is currently assigned to such and such thread ID. If we run this, if we run this string is going to run for 104 loop iterations, because that's reasonably small enough that it wouldn't flood our terminal. We run this for 104 loop iterations, and if we give it 4 threads, it will be divided into 4 blocks of 25 consecutive loop iterations. So loop iteration 0 to 24 is being executed by thread 0, and then because there's no guarantee that the order in which the threads is, there's no guarantee in which the order of the threads will print to the screen in order. Here it jumps straight to thread 3, doing its loop iteration 75 to 99. So this is an example. Generally, if there are n iterations and we have t as a thread count, it's going to be n over t consecutive threads assigned to each thread. If you have a situation where, say, the first couple of for loop iterations are, say, easier to execute, say they take less time, then you might want to consider different schedulings. So here's an example. Say, for example, we want to parallelize this for loop, but this f function is more expensive the larger I becomes. Or it could be the other way around, where if I is small, f of I is easy to calculate. In this case, we would be giving more work to thread 0. So this is where we might want to have round-robin partitioning come into play. If I could visualize what this would look like, pretend each circle is representational of the amount of work that a for loop iteration has to do. So if there are 4 threads, we would divide this into blocks of 4, and then suddenly thread with the ID of 0 gets all the work, and then the thread with ID of 3 gets barely any work. That's not good. It means that the other 3 threads would have to wait for thread 0 to finish because it somehow got all the work. If we did this instead. Now we have a situation where it's a bit more balanced. So thread 0 is doing this much work, this much work, this much work, and this much work combined. It's a similar deal with threads 1, 2, and 3, so it's a lot more balanced. This is round robin. We can implement that by using the schedule clause. So this is the general syntax of the schedule clause. We have a type that's going to be one of 5 keywords. And then some of the types will take in a chunk size. So let me explain that. If we have schedule static, that's going to be... If we have schedule static and we don't specify a chunk size, that's going to be no different from the default. If we have schedule static 2, that means we have a chunk size of 2 consecutive threads. And by the looks of it, this looks like that round robin. That looks like round robin. In fact, if we have schedule static 1, it would be round robin. So, yeah. Only static, dynamic, and guided schedules can have a chunk size. Some of these types don't need a chunk size. So the chunk size is how big a block of consecutive for loop iterations is. Dynamic is a little bit interesting, and here we don't know which threads will get what for loop iterations. Not ahead of time, at least. But I'll explain each one a little bit. The static schedule type assigns chunks of chunk size to each thread in a round robin fashion. And omitting a chunk size will just result in the default. If we have 100 iterations divided over 4 threads, and we have a chunk size of 0, thread 0 is going to have iterations 0, 4, 8, 12, 16, and so on. Thread 1 gets iterations 1, 5, 9, 13, 17, and so on. Thread 2 gets iterations 2, 6, 10, 14, 18, and so on. Thread 3 gets iterations 7, 11, 15, 19, and so on. In a dynamic schedule, iterations are also broken up into chunks of chunk size. But here's the thing. Each thread is given a chunk. When it finishes a chunk, it requests another chunk from the runtime system. In one of the past videos, I mentioned the example of the professor and 4 TAs who had to grade 100 exams. I posited the possibility of what if one grader finishes faster. Well, I'm gonna also bring up the flip side of that. What if one grader finishes slower because they had to grade a test from someone who had really poor handwriting and they spent most of the time just deciphering what they wrote on the test? Well, in this scenario, you would be better off not, because there are 5 graders in the scenario, the professor and the 4 TAs. It would be better to do it like this. If you're doing dynamic scheduling and you had a chunk size that was smaller than 20, say it's size 5, each of the 5 graders would get a packet of 5 tests to grade. When any one grader is done with the 5 tests, they grab another packet of 5 tests to grade. It doesn't matter whether anyone is faster or slower, especially when we have someone who grades faster or slower than others because of what happens if someone has really poor handwriting. Or, I guess, what if there was a mad lad who looked at the exam, answered nothing, submitted the test as it was? That would make your life easier as a grader because that would be an immediate 0. You can just mark it as 0, move on to the next one. On the other hand, there is that scenario of what happens if someone has really poor handwriting and you spent more time deciphering the handwriting than you did actually grading. So that's what I mean by what happens if one grader finishes faster than the others, or if one grader finishes slower than the others. In that scenario, you want a dynamic schedule, and that's what the analogy was. It's an analogy on dynamic scheduling. There's also the guided scheduling type. I'll get to that in a little bit. New chunks, but first, in the dynamic scheduling, new chunks are given to threads on a first come first serve basis, which is good for the exact scenario I just described. When loop iterations don't take a uniform time to complete. However, since the ranges are not allocated ahead of time, there is some overhead associated with assigning chunks at runtime. It would be like this. Imagine the professor and the 4th graders were grading in a room. They had a table with all the tests, and that overhead would be just running back and forth to grab a new packet of tests to grade. The guided schedule is similar to the dynamic schedule, except the chunk size decreases over time until it reaches the size of chunk size. If you don't specify chunk size, then it's going to decrease all the way down to 1. This is more useful if you have later for loop iterations that are more expensive, more computationally expensive. They take more time to execute. I'm not going to get into the runtime and auto scheduling types. Runtime is based on using your environment variables to specify a scheduling type. We're not really going to do that for our programs, but just in case you want the information, it's on page, hold on. Just in case you want information on what the runtime scheduling type is, that's on page 253 and 254. For now, we're going to move on to what scheduling type do you use? Well, it all depends. The two questions that come to mind is what scheduling type do you use and how big do you want your chunk size? A few things to keep in mind. There is some overhead with using the schedule clause. A dynamic schedule will have greater overhead than using a static schedule, and a guided schedule will have even more overhead than a dynamic schedule. If you feel like you're getting good enough results using just the default schedule, you don't have to worry. But if you feel like you could improve the execution times because you feel like the default schedule is holding you back, then it's worth experimenting with different scheduling types to see what you get. It can also be as simple as rewriting your code so that you only have one fork and join instead of one for every for loop iteration. But this is the scenario with nested for loops. Here are the scenarios where it's useful to consider different schedules. If each loop iteration takes about the same amount of time, the default is fine. If the cost of iterations increases or decreases linearly as the loop executes, you may want to use a static schedule with small chunk sizes. If you cannot determine the sizes of the if you cannot determine the cost of for loop iterations in advance, try a runtime schedule. I think that should be a dynamic schedule. But yeah, these are things that you would experiment with. So anyway, that's the end of this video. You now have not only a short answer question 2, but your first programming assignment. If you have any questions about the homework or anything about the class, you are welcome to email me, or possibly, if you prefer a Zoom meeting, you can schedule a Zoom meeting. Other than that, that's going to be it for me this week. This should be uploaded sometime this Thursday. And with that, maybe next week we can start looking at P-threads. So yeah, that's it. See you next week.